we are going to be treating now is radioactivity. Now, radioactivity involves electromagnetic radiation that are emitted due to unstable nuclei. Remember, nuclear chemistry or radioactivity is basically dealing with the nucleus, and unstable nucleus tend to disintegrate to form nuclear materials. Now, there are types of radioactivity. Number one we have here is natural radioactivity. Now, natural radioactivity deals with spontaneous disintegration. That is, that disintegration does not need to be infused or does not need to be enforced by any external agent. It is a natural thing, that is, it is spontaneous and it occurs on its own. An example of an element that undergoes natural radioactivity is uranium. A reaction that involves uranium undergoing natural radioactivity is presented below. When uranium-238 undergoes a reaction to form thorium and helium particle, or you say alpha particle. So this will be 234 and this will be 90. And if you cross check, both the atomic number and the mass number are both corresponding to each other. So this is an example of natural radioactivity. Now, the number two type of activity is artificial radioactivity, and it is also called induced radiation, which simply means, by the word induced, you should know that these nucleus are actually stable and they don't undergo radioactivity normally, but it can be induced on them by bombardment of nuclei with accelerated subatomic particles, and includes artificial radiation by nitrogen. Here is an example of artificial radioactivity whereby a stable nucleus of nitrogen is being induced by accelerated bombardment of helium particle, and it gives oxygen and hydrogen. This is a typical example of artificial radioactivity. Elements that undergo natural radioactivity are elements that have atomic number above 84 in the periodic table. So any elements that you see that is below 84 is likely going to undergo artificial radioactivity, if it is to undergo any radioactivity at all. Now, let's go over a brief history of radioactivity. In 1896, a scientist named Wilhelm Roentgen, his name is Wilhelm Roentgen, discovered X-ray, and this was the first step to the discovery of radioactivity. And he discovered it by examining rays emitting from the outside of a cathode ray glass tube, and this was how X-ray was discovered, also called the Roentgen ray. In that same year, Anton Becquerel, his name is Anton, he was the guy that discovered radioactivity. Anton Becquerel discovered radioactivity. He did so in an experiment where he discovered that uranium emits a ray onto a photographic plate in the absence of sunlight or other forms of energy. So no external energy was induced in uranium, but yet it was emitting rays of photographic plates. That was how he discovered that this is actually something new. However, the name radioactivity was given by Marie Curie. She was the one that gave the name radioactivity, and Antonio Becquerel was the one that discovered natural radioactivity. Now, I wouldn't want us to forget about nuclear transmutation. Nuclear transmutation is a process where radioactivity is resulted from the bombardment of nuclei by neutron, proton, or other nuclei. It's just like artificial radioactivity, and this was discovered by Rutherford. So it was discovered by Rutherford. Please don't forget that. Next up, we're talking about radioactive decay. Now this deals with how radioactive elements are balanced. And before we can solve these questions, we need to know what radioactive particles are. Now we have different kinds of radioactive particles, which includes the alpha particles, beta particle, gamma, neutron, proton, positron, and so on. So today we'll be learning about their symbols, their sign, and their charges. For alpha particle can be represented as this, with 4 mass number and 2 atomic number. It can also be represented as the helium particle. This should be 4 and this should be 2. So this is our alpha particle, and it is positively charged. Positively charged. That's the charge of the alpha particle. Now for our beta particle is represented as an electron, or you can say a negative electron. So this is the beta particle with 0 mass number and negative atomic number. Neutron particle is a particle that has no atomic number. So its mass number is 1, while its atomic number is 0. So that's a neutron particle. Our proton particle can be represented in 2 ways, but having the same equivalent of the mass number and the atomic number. So either you are representing it like this, with mass number of 1 and atomic number of 1, or you are representing it with the hydrogen atom, with mass number of 1 and proton number of 1. Now, the next is the positron. The positron, unlike the beta particle, is a positive electron. So it is represented the same way, but having a positive atomic number. So the beta particle has a negative atomic number, while the positron has a positive atomic number. Next up, we'll be talking about the gamma particle. The gamma particle is the natural particle with the highest penetration power, and most times can be stopped by lead block. Now, it is sometimes formed from the reaction between a beta particle and a positron. What do I mean? When a beta particle with the negative atomic number reacts with a positron with a positive atomic number. Now these two particles will cancel each other to produce gamma particle with 0 atomic number and 0 atomic mass respectively. So this should be represented as 0 and 0. So having laid down the basic knowledge of radioactive decay and nuclear chemistry balancing, we can actually solve these questions. Now we are being asked to find the value of x here and the value of x over here. So this is just the principle, the simple principle you can use for nuclear reaction is that the both sides should be equal. That is, the mass number of the right hand side should be equal to the mass number of the left hand side, and the mass number and the atomic number of the right hand side should be equal to the atomic number of the left hand side. Now the atomic number here is 92, while the atomic number here is 90. So subtracting 90 from 92, you'll be having 2 over here. Whereas subtracting 231 from 235, you'll be having 4 over here. So if you are being asked what emission is this, this is an alpha particle decay or emission. This should be an alpha particle. The next one we have here is oxygen plus neutron particle, which will give us an element which emits helium particles or alpha particles rather. So the first trick here is to know what a neutron particle is. And according to the fundamental knowledge which we laid down, we got to discover that a neutron particle can be represented like this. So back to our question, our neutron particle we placed here. It's a mass number of 1, atomic number of 0. Now, remember our fundamental principle which we laid down, that to balance a nuclear reaction, the right hand side must be equal to the left hand side in both atomic number and mass number. So in total, the mass number we have for the right hand side, which is the reacting side, is 17. That is 16 of oxygen plus the neutron particle, which is having just 1 mass number, will be 17 for the reactant side. Now for the product side, we have just 4 mass number here, so it should definitely be 17 minus 4. that will be 13. So right up here we have in 13. Now for our atomic number, for the right hand side, which is the reactant side, we are having atomic number of 8. While over here we have atomic number of 2. So when you subtract both sides, that will be 8 minus 2 is equivalent to 6. So over here we'll be having 6. So at the end we'll be having carbon 13. So this is carbon 13. That's our final answer. Alright guys, that'll be all for now. Please subscribe and hit the notification button so you'll be able to see our next upload on half-life calculations and decay constant. Have a nice day.